for a uniform velocity profile. That is, if velocity profile were the same at every point and it has a value of v, then volume flow rate Q is equal to V. That is true only if the velocity is uniform across the cross section. For a general non-uniform velocity profile, we wrote Q is equal to integral r equal to 0 to r equal to r Vz dA. That's what we wrote. And then we saw the derivation of how this dA in a radial sense is equal to Vz of r times 2 pi r dr. That's the geometrical derivation I showed at the end of last lecture. You can see towards the last 5 minutes of the previous lecture to see how dA can be written as dA is equal to pi r plus dr squared minus pi r squared, which gets us 2 pi r dr. Okay, so this is where we stopped last time, and what we want to do is, if you have, let's say, a volume, an arbitrary volume, first I'll draw that, and then let's say it has multiple inlets and multiple outlets. Some kind of a fluid system where you have multiple inlets and ways in which fluid can leave the system. Okay, so arbitrary system, which we'll call control volume. So we are trying to understand the net mass flow in and out of the system, as well as the accumulation of mass within the system. That's why this whole chapter is called control volume analysis. We are trying to do a mass balance on an arbitrary control volume. Okay, so if you had velocity, let's say here, and we discussed how we talked about how area is represented as a vector, and usually the outward drawn normal is used to denote the sense, So it's like saying, if I have this area, let's say I have this cross section area, this area is represented as A, the area, multiplied by the unit vector. So area vector is A, the magnitude, multiplied by n cap, the direction. So this outward drawn normal is n cap, and the magnitude of the area is A. We draw it this way, such that if you have a flow velocity in this sense, V dot A is V dot n cap times A is negative if this is an inlet, and V dot A, which is V dot n cap times A, is positive for an outlet. We always adopt a convention such that area is drawn as an outward drawn normal, which will make inlets negative and outlets positive, meaning the outflow, this is n cap and this is velocity. So outlet is positive, that is V dot A. V dot A is positive, and for an inlet, V dot A is negative. Okay. The reason I write it this way is over here I have Vz dot dA. So when I want to calculate flow rate Q, which I write as integral R equal to 0 to R, Vz of R, 2 pi R dr. I'm going to generalize this by writing this is Vz of R times dA. Okay. And to write this in vector form, I'm going to write this is V vector dot n cap times dA over the cross section that I'm interested in. Now, please take a pause, look up. I'll explain this statement because this is kind of crucial. No need to write. I'll give you time. Okay. So what I'm doing here is to say I take any cross section. The velocity coming out of this flow. Let's say the velocity is not directly aligned with the normal vector. Let's say the velocity is in some direction. The normal vector is in some other direction. Now you can think of what part of the velocity will actually contribute for the flow to exit this cross section and what part of this will only slam into the wall up here. Can you tell which which component contributes to the flow rate going out of this cross section? Cosine theta. That will be cosine theta or the dot product. That is, if I want to know how much is going in this direction and how much is going perpendicular to the direction, V dot n is what I care about. This is the relevant component of the velocity which contributes to an inflow or an outflow. That is why we have V dot n, which is the cross section or the velocity that's leaving the cross or perpendicular to the cross section multiplied by the area itself. Okay. This expression is, again, my friend, take a pause. I'll give you time to write. Okay. I'll repeat what I said. I'll let you write. Okay. This expression is not just restricted to circular cross section, or it's not even attached to any particular geometry or shape of the cross section. It can be a triangle, square, whatever cross section due. This integral holds. So we call this the expression for flow rate across an arbitrary area. So when we want mass flow rate, okay, when we want mass flow rate, if this is volume flow rate, how do we obtain mass flow rate from here? How do you go from volume flow rate to mass flow rate? Multiply by density. Multiply by density. So if this is Q, we will write mass flow rate across any cross section in this volume is integral density times velocity in that cross section dot n cap, the local area or the local normal vector, multiplied by dA. And then if this were a circular cross section, we'll substitute 2 pi r dr and do the integration. And we'll do some examples to reinforce that. But this expression is what you really need to be able to write down or to calculate what is the mass flow rate across a cross section coming in or exiting a control volume. The big difference is in thermodynamics, they always told you how much mass is coming into a system or leaving the system. They gave you a number directly. In fluid mechanics, we don't directly handle the mass flow rate, we handle velocity, and from velocity we compute the mass flow rate, and that's how you compute this. Okay, so this is the time I'm going to give you to write this. What you want to write down next to this m dot, I'll put it in words. Please make a note. So this expression allows the calculation of mass flow rate across any exit or entry to the control volume in terms of the number one velocity profile V of R and cross section area A. Okay, so please make a note of this. I'll keep quiet for a minute. We good? Yeah. So some terminology for you to kind of observe here. This arbitrary system, we'll start calling it control volume. It's the bulk. Control volume. We'll use CV to denote that. The surface bounding the control volume or the surface separating the control volume from the rest of the surroundings, we call that control surface, CS. So in your thermodynamics, you learn system and surrounding, right? System is loosely what we call control volume, and surrounding is everything outside, and the surface separating the control volume and the surrounding is your control surface. Okay. Now, in your control surface, there are some portions where there is an entrance or an exit for flow to come in and go out. Everywhere else, there is a wall. Okay. Everywhere else, there is a wall. So let me ask you a question. Okay. Let's say at this point, the normal vector is drawn this way. What is V dot n at this point? Zero. Why? Because velocity is zero. You can't have a flow penetrating a wall. The reason it's called a wall, it's because it can't be penetrated. Right? So the velocity here is zero. So regardless of what direction the normal vector locally is, V dot n is zero along walls. If fluid can't get through, V dot n is zero. That's another way of saying mass flow rate across a wall is zero. Okay? If it's a, let's say if it's an inlet, okay, you have n cap pointing this way and V dot velocity pointing this way, you would have V dot n to be negative, which means it's an inlet, or if it's an inlet, V dot n must be negative by convention. Okay, just reinforcing this. And same thing for outlet. Let me clean this. If this is an outlet, n cap is drawn this way, velocity is pointing outwards, V dot n is positive, that is for an outlet, and if it is an outlet, V dot n is positive by convention. Okay, so now we are going to take this equation. We're going to take this equation. Instead of this, we are going to write integral CS rho V dot n dA, and these are portions of the CS where V dot n is negative. That's what we call inlets. There could be multiple inlets, but what I'm saying is whatever we call as the net inflow or the mass influx is nothing but the integral over the control surfaces where you have inlets minus integral over rho v dot n dA where you have v dot n positive or outlets.
That's him not in.
Which one?
Like just that is you're describing them,
This one?
both of them.
So this is m dot in, this is m dot out. Thank you. So today for the rest of the class, we'll just do examples on this. So to do mass conservation, examples on that, and then next lecture we'll do momentum conservation. Okay. Just to reinforce this so far. Okay, now drop your pencils, look up please. What about this term? What is the rate of change of mass? How can we describe that in terms of what is contained within the volume? How much mass is contained within this volume? Like, give me an expression. If I ask you to calculate how much water is in this, how much mass of water is present in this bottle, what will you do? You will ask me for the dimensions of the bottle, calculate its volume, you look up the density of water, and you will multiply them together to get the mass of water. Right? You can all agree that mass is density times volume, correct? Mass equal to density times volume. We can all agree. Now, I told you this is, again, people who are writing, take a break. Okay, I'll give you time and tell you what to write down. This we need to talk, okay? So if you take an arbitrary volume, how will you compute the total mass in that volume? If it's a cube, what's the volume? It's side cube. If it's a sphere, you know, pi by 6 d cube. But for an arbitrary volume, how do we get volume? Integrate. You integrate. That is the volume of the volume is integral dv, or this can be written in Cartesian as integral dx dy dz for the chosen volume, or it can be written in other coordinates like spherical polar r squared sine theta dr d theta d. We are not going to do very serious triple integrals here, so let's not go there. We just want to make the point. Volume is an elementary volume integrated over a big space. Okay. Now, if I take an elementary volume, that is dV. What's the mass of this elementary volume? Can I write that to be density times the volume? Right? Density times the volume. And then if I want the total mass M, that would be integral over the control volume rho dV. Take a good look at this expression and tell me if this makes sense to you. All I'm saying is I'm taking a small package or a small portion whose volume is dV and whose mass is rho times dV, and then integrating over the entire volume. That's all I'm doing here through this integral. Take a moment, tell me if that clicks or that makes sense. Right? Just simple math. Density multiplied by an elementary volume integrated over the entire volume. This density could be a simple constant or it could change with position. Whatever it is, we are multiplying and integrating over the volume. Okay. Yeah. So can I take this expression and write this is the rate of change of mass rho d. Can I write this? Instead of mass, I'm representing it as an integral. I'll give you some examples to make sense. I'm just replacing mass with integral rho d. Okay. Think about this example for me. Let's say you have a balloon and you are blowing air into the balloon. What is the how will you estimate the rate at which mass is entering the balloon? Or in other words, how will we get mass in? That will be the velocity with which you inject air. So that will be integral v dot n dA over the single surface that you have here, CS1. What is the rate of change of mass of this balloon? Let's say you inject air at a certain density is constant. How will you calculate the rate of increase of mass of this balloon? It would be density times the rate at which the volume of the balloon increases, right? So this system is a rare instance where you are having an increase in mass. Okay, you are having an increase in mass, so this number is going to be positive. This number is going to be positive, and you're going to evaluate this, and this is equal to this is going to be equal to this mass in. Okay, let me give you another example. Let's say we have this nozzle. This is like a problem in one of your exam or your mock exams. Let's say you have a certain velocity in this section. We'll call it V1 and another velocity here, V2. Okay. If I say the fluid we use is incompressible and we also have steady flow, then can you think and tell me what is the rate of change of mass or d over dt integral rho dV for this system where my control volume coincides with the shape of the nozzle? What I want from you is tell me what is the rate of increase or rate of change of mass for this example. Steady flow, water comes in, water exits, and it will accelerate because of it's being a nozzle, the cross section is dropping. What is the rate of increase of mass?
0.
Why 0?
Because it's steady flow.
It's steady flow, meaning whatever comes in must exit, and since it's incompressible, it cannot accumulate. So the rate of increase of mass must be 0. If it cannot accumulate, it has to exit, right? So this is 0 because this is steady and incompressible. Okay, so for steady flow problems, this number is 0 for steady flow, meaning what comes in must be balanced by what leaves. Okay, so to make it a little bit pretty and neat to keep in reference, let me rewrite it and then maybe start an example. So we have derivative with respect to time over the control volume rho dV is equal to integral over the control surfaces rho v dot n dA, where CS includes CS inlets and CS outlets. CS inlets are defined by V dot N being negative and CS outlets are defined by V dot N being positive. So this equation is what you need for problem solving and do mass balance on fluid systems. Okay, and let's see some examples. Problem 5.14, if you have the book with you. Problem 5.14. Okay. So I would keep this in my equation cheat sheet or cheat sheet, for the exam. And all problems usually will involve applying this equation to get something about the velocity as well as coupling this with momentum balance. We will be doing problem 5.14. So after I complete this unit, we are technically ready for your project. We'll talk about that. I prepared something to share. Water at 0.1 meter cube per second and alcohol at 0.3 meter cube per second are mixed in a Y duct as shown. What is the average density of the mixture of alcohol and water? So nothing else is given. First thing is we are given water and alcohol, two liquids. So we'll assume they are incompressible, even though that's most generally the case. Are we given anything about this flow being steady or unsteady? We're not told anything. It just says it's like a mixing duct where you have two streams mixing on the other side and coming as a single stream. Okay, so we'll assume it's steady. Okay, so if you are done noting down this, I'm going to start writing some steps. Are we good? Yeah, okay. Okay, so we have a Y duct. Okay, I'll draw this like here. So you have water coming in here at 0.1 meter cube per second, water, and then 0.3 meter cube per second of alcohol. Listen please, and over here you are getting a mixture out, okay, mixture out, and we want to know what's the density of this mixture. That's the problem, okay? So step one, draw or mark the control volume and control surfaces. Mark the control volume and control surfaces. You want to designate something over which you are doing this mass balance. So I will choose the volume that coincides with the Y duct as my control volume, and the dotted line shows the control surface. So this is my control volume and this is my control surface. It's really important you have a clear idea which is your control volume so that you can apply those equations correctly. Okay, so start with marking the control volume and control surfaces. Okay. Step 2. Write the equation for mass balance for this control volume. What is that? It's basically this equation. Integral over, different derivative with respect to time, rho dV over the control volume is equal to integral over the control surfaces, rho v dot n dV. Now this is where we are going to unpack how to use this expression. So far I have just shown you this expression. Step 3. Step 3, we have steady flow. Steady flow, which implies no change in mass inside the control volume. And what's the consequence of that? It means the derivative with respect to time, integral rho dV over the control volume is 0. By recognizing steady flow, you are setting the left side to 0. With me so far? Yeah. So step 4. Step 4, we have 0 equal to integral CS, integral over the control surfaces, rho v dot n dA. Identify inlets, sorry. Identify inlets and outlets. Split the integral over CS equal to integral over CS inlet plus integral over CS outlets. So we have one inlet here and 2 is also an inlet and 3 is an outlet. Okay, take a pause, look up, we're going to do this. So if I look at integral over the control surface for inlet 1. Inlet 1. What is coming through inlet 1? Water. So I have density of water multiplied by B dot n cap dA. Okay. Dot n cap dA. Right? So with this write this is density of water multiplied by B dot n cap dA over CS1. Now we do know that this is flow rate, that is this expression is flow rate of water entering through section 1, but we did adopt the convention B dot n is negative, so this would be rho w minus 1 times q1, where q1 is 0.1 meter cube per second. We are given already the flow rate. If we were told in terms of velocity, we would have done that calculation. But we just use the flow rate directly once we pull this expression or pull this density out of the integral because we have an incompressible fluid. So I have minus Q1 or minus rho W times Q1 and keep it like that. And what about inlet 2? If I write this for CS2, which is again another inlet, I have rho alcohol times V dot N dA, that is equal to rho alcohol multiplied by minus Q2, or this is minus rho A Q2. The main thing I'm adding is whenever it's an inlet, I'm adding a negative sign so that the math will work out correctly. And what about section 3? Integral CS3, which is an outlet, rho unknown, which is what we are trying to solve for, B dot N dA. So that is like writing integral rho u times integral B dot N dA CS3. So this is rho u times Q3. Note the plus sign because it's an outlet. This V dot N is positive, so we have the plus sign. Okay. So let's bring this together here. I have 0 equal to minus rho water Q1 plus or minus rho alcohol Q2 plus rho unknown Q3. So rho unknown is rho water Q1 plus rho alcohol Q2 divided by Q3. What is Q3? How do we get Q3?
Add the two together.
We are mixing two volumes, right? That's the net volume. So Q3 is Q1 plus Q2. So this is like a weighted average where you have raw water Q1 plus raw alcohol Q2 divided by Q1 plus Q2. So that's your effective density of the alcohol water mixture stream that's exiting the Y duct. And do the calculation if you want. So this would be 1000 times 0.3 plus 800 times 1000 times 0.1 plus 800 times 0.3 divided by 0.4. Which is 250 plus 600, 850. 850 kg per meter. That is the density at the exit stream. A quick recap. We chose a problem in which the volume flow rate was already given. Now, instead of volume flow rate being given to you, we are going to be seeing a velocity profile given, and we are going to do the integration. Okay. So this was problem 5.14. Problem 5.14. Next, we are going to try problem 5.17. If you have your book with you, please look up problem 5.17. Take a moment, please read this. Okay, so let's talk about the problem. We have a pipe flow. You have an inlet stream where there are three sections, or if you think of it as a circular cross section, the core is moving faster at 30 meters per second, whereas the outer periphery is slower. And do we know the velocity there? Jet velocity of 30 meters per second. Okay, so we need to figure out what's the velocity of the periphery or the entrained flow. What we are told is a little bit downstream, the faster and the slower streams mix together and result in an average of 6 meters per second that's uniform across the cross section. So the question is, what is the velocity of the entrained water? I mean, they are asking flow rate, but first we'll start with velocity and then later get flow rate. Any thoughts? How would we think about this? What should be your control volume? Let's make that selection first. It should be a volume that roughly coincides with this plane and this plane, basically a cylinder which runs from this point to this point of the same cross section. Okay? With me, that makes sense. That we should have a cylindrical control volume which coincides with the pipe. In the inlet cross section, do we have a single velocity or do we have different velocities? We have two different velocities, the inner from 0 to R and the outer from R to R1 or something. Right? The inner core has a velocity of 30 meter per second. The outer has a different velocity which we have to determine. What about on this side? Do we have a single velocity or a different velocity? For this side, for the outlet. With a uniform velocity or does it change with cross section? It's uniform, right? It's just a single value 6 meter per second. Okay. So two things. First is the control volume coincides with the pipe, is of the same cylindrical shape. Number two, at every control surface, the velocity is uniform. So we just have to take the velocity and multiply by the cross section to get the flow rate. We don't have to do any integration. Okay, so let's do this calculation. Can I take this down? Yeah. So I have a pipe. Okay, and I draw a control volume which coincides with the pipe. And to show you that this is a pipe, I'll mark an axis. Okay, at this surface, what's my velocity? 6 meter per second. Okay, at this surface, from 0 to some radius, I'll call it R1. I have 30 meter per second, and from R1 to R2, we have some unknown velocity. We'll call it V. Okay, so step one, mark the control volume and identify inlets and outlets. This is an inlet. This is an outlet. Quick question. This is a wall. What is V dot N on the wall? 0. Just to make sure we all remember that. Okay. All right. Step 2. We have partial derivative with respect to time. Integral over the entire volume, rho dV, equal to integral over the control surface, rho V dot N dV. Since we have steady flow, this implies there is no accumulation. So this term is 0. So that gets us integral CS inlet rho V dot N dA plus integral CS outlet rho V dot N dA equal to 0. Okay, one more simplification. Density is constant and same for both inlet and outlet. So which implies you can drop density from this equation. Okay, so integral control surface inlet V dot N dA. Look up please. This control surface inlet is actually having two zones. So if you see from the side view, there is the inner zone where the velocity is faster, 30 meter per second. And then there is an outer zone where velocity is slower, and we are trying to determine that. Okay, so I will split this as CS inner plus CS outer. So for the inner, I have 30 meter per second uniform. Do I need to do integration? Can I just write this is, so if this is like writing V1 or yeah, V inner multiplied by integral dA. Oh, sorry. Okay. This is minus 30 meter per second times A inner. Is that okay? Because it's an inlet, we get the negative sign. Because the velocity is uniform, this is just integral dA that gets us area of the inner circle. Right? So you get, if they tell us what's the radius. So this is minus 30 meter per second times 0.01 meter squared. This is given. So that gets us minus 0.3 meter cube per second. Okay. Yeah. What about the outer? The outer velocity is not known, we'll call it V, multiplied by minus 1 or minus B times A outer. This A outer. The total cross section area is 0.075, which means the outer must be 0.065. So this is minus B times 0.065. So the value is minus 0.065 times B. What about outlet? Integral CS outlet V dot N dA is equal to plus 6 meter per second times area of the entire cross section, which is 6 meter per second times 0.075 meter squared, which is how much? What is 75 times 6? 0.45 meter cube per second. So for this expression, I have minus 0.3 meter cube per second minus 0.065 V meter cube per second plus 0.45 meter cube per second equal to 0. Now you have to solve for V. So that's like writing 0.065 V equals 0.15. So V equal to 0.15 divided by 0.065 or 150 divided by 65 divided by 65, which is a little more than 2 point something meter per second. Something like 2.3 meter per second. So this portion is coming in at 2.3 meter per second. So what's the flow rate associated with that portion? Q outer would be V multiplied by A outer, which is 2.3 meter per second multiplied by multiplied by 0.065, or in other words, it's nothing but 0.15 meter cube per second. Still no integration. We took uniform velocities and got away without doing any integration. Are we okay? Any questions? Making sense? Yeah.
I missed the last part. How did you get the,
This one?
yeah,
So I took this equation where I have the inlet flow to be negative 0.3 minus 0.065 times V. And then the outlet flow is plus 0.45, and add that all of this should add up to 0, which allows me to solve for V. Okay, and then to get the flow rate, I just took V multiplied by the area of the outer portion, which is 0.065. This equation is also a balance for Q. So you can, instead of calling this, you can call it Q outer, which is simply 0.15. 45 minus 30. Okay. So now we'll try to do this with some integration. Okay. Unless there are no questions. Problem 5.22. That's our next problem. Problem 5.2. So this was problem 5.17. Problem 5.22. Please take a look. At the entrance to a 3 feet wide channel, the velocity distribution is uniform and with a velocity v. That is the inlet. further downstream, the velocity profile is given by u equal to 4y minus 2y squared. That is saying it varies parabolically from the bottom to the top as 4y minus 2y squared, where u is measured in feet per second and y is in feet. Determine the value of v. Okay. Take a moment, look up. Don't think of this problem. I mean, in this mass balance, don't get too bogged down by mathematics. Think what's happening intuitively. This is water, incompressible. If water comes in at a certain flow rate, it has to leave at the same flow rate if it's a steady flow, right? So if you compute what's the flow rate coming in, what is flow rate? Velocity times cross section. And what is cross section here? This is a three feet wide channel. Like it's a channel. If you look from the top, the width is 3 feet. So they are showing you the side view. So how much is the cross section? 3 times 0.75, width multiplied by height, right? So 3 times 0.75 times 3 should be equal to the flow rate on the other side, which is the velocity multiplied by area. Except this velocity is not uniform, so you can't just multiply velocity and area. You have to integrate along the height. So what is the area of this channel? If you express it in terms of elementary area, dy times what? It should be dy, a small length, multiplied by the width, which is uniform. W times dy, right? So you integrate this velocity over the height. That's intuitively the steps. Okay, and now we'll put it in math. Okay. Steady flow, so there is no change in mass. Inlet velocity is uniform, that's easy. Outlet velocity is non-uniform, so you do integration. That's all. Okay. Why don't you try this and then we'll converge and check our answers. Can I take this away? No. So I have 0 equal to V times, what is the height? 0.75 times 0.75 feet multiplied by W, where W is width of the channel given as 3 feet. This is inlet, so I have to add a negative sign, plus integral 0 to 1 feet, y equal to 0 to y equal to 1 feet, 4y, sorry, what was it? 4y minus 2y squared times w dy. I intentionally skipped so many steps to get here. What I want you to do is to really look at this and make sure you understand it, or make sure if this something not clear, tell me. Yeah,
Why would you put W in this variable if you know the value of it already?
because I know it appears in 2 terms, so I'll just cancel it and do one less arithmetic step. which is like reducing some chance for mistake. Is this making sense to you? This is uniform velocity. So this is uniform velocity. Uniform velocity. So we can just do velocity times area. This is non-uniform velocity. So we'll have to do velocity as a function of y multiplied by w dy integral y equal to 0 to 1 feet. Okay, so I can up this w. So if I want v is going to be integral 0 to 1 4y minus 2y squared dy divided by 0.75. Can anybody tell me the value?
1.773.
1.773 meter per sorry, feet per second. Is okay? I mean, as we do more examples, what I'm essentially doing is to kind of keeping steps, but also making sure that you internalize this thinking so that you can also see it as an obvious thing and not have to do every step all the time. Is everybody okay? Yeah, can you? Yeah. So let's do problem 5.23, which is actually a very practically relevant example, I would say, because let's say you're managing a air duct like a HVAC duct. This is how in the real world you would estimate flow rates. So look at problem 5.23. So what they have given here is the cross section of a rectangular duct is divided into 16 segments. The axial velocity measured in feet per second in each smaller area is given in the figure. Estimate the volume flow rate and average axial velocity. So if you have a large duct, okay, in practice, nobody will measure the flow rate of a large duct with any flow meter. What they would do is discretize this cross section into like segments, like 16 segments here, have a velocity probe, stick the probe at each segment at the center of each segment, read out the velocity in this each segment, like here, 16 values. And then what you do is you estimate the flow rate in each segment and then you sum everything up. So what is the flow rate across the segment where you have 3 feet per second? Assuming the 3 feet per second is uniform across the square. Just tell me the expression, you don't have to compute right away. So this is 16 by 20. If you divide 16 into 4 equal segments, that's 4 by 5. Right? So you have 3 feet per second multiplied by 4 inches multiplied by 5 inches. Of course, you have to convert the inch to feet. Or you have to divide by 12 squared. So the flow rate across the first segment is, or flow rate across any segment is, so what is the flow rate across any segment? I'll call it Qi. That would be Vi multiplied by 4 inches multiplied by 5 inches divided by 12 squared to convert to feet. Yeah. So if I want the total flow rate, Q total, that will be summation over each segment, and there are 16 such segments, right? 16 segments, right? So this is nothing but 1/3, and then okay. So 20 divided by 144 multiplied by sigma Vi for all the 16 segments. The operator would essentially have like holes drilled at the walls, insert a probe at the first segment, read out the value, push the probe further, read out the value, push it all the way to the third and fourth, and then move to the next segment, next segment, next segment. This is how practically we will have a value, 16 values. Then you can do the calculation of what's the total flow rate. Are you able to think about this? Okay, so estimate total volume flow rate is summation of all the velocities multiplied by the area of each segment. So I'll write this sigma Vi times area of each segment. How do you define a total average velocity for the entire duct? How to think of an average? What is average? So average is something you can think of as each segment has a slightly different velocity, right? Can we name or can we identify a single velocity which can be considered to be uniform across the entire duct, not across each segment, but an entire duct? So I'll rewrite this. Yeah, I'll write it here. Okay, so Q total equal to area of each segment multiplied by the sum of all the velocities in each segment. This is also equal to area total multiplied by an average velocity. So V average would be area segment multiplied by area divided by area total times sum of all the velocities in each segment. This is nothing but 16 times area of each segment. So average velocity is nothing but 1/16 of the sum of the individual velocities. It's okay? Yeah. Okay. Now in the last 9 minutes, what I wish to talk about, we saw how to use the equation for mass balance to compute these velocities or flow rates as necessary. But answer this for me, when a fluid or when fluid leaves a system or enters a system at a certain velocity, in addition to bringing mass, what else does it bring? So in every unit volume of fluid, what all quantities that it does it bring? You bring mass. Along with mass, what other inherent properties does fluid have? Thermal energy, temperature. What else does it bring if it comes at a certain velocity? Momentum. It brings force, it brings momentum, right? You can think of as a fluid crossing a surface not only contributes to, so writing that, like listening time, you don't have to write this because I'll say this again at the top of next lecture. So a fluid or fluid when crossing a controlled surface brings mass. Okay, that mass we wrote as integral rho v dot n dv. Right? It brings momentum. How do we write an expression for momentum that the fluid brings due to its velocity? What is this quantity? What is the units of this quantity? Volume flow rate. Volume flow rate. This is volume per time. Right? So by taking volume per time and multiplying with mass per volume, you are getting mass per time. Okay? So if I ask you the question, a tiny packet of fluid whose volume we'll consider V. Okay. What is the mass contained in this fluid? Mass contained in this fluid or this parcel is rho times V. What is the momentum contained in this? You have a little tiny particle of fluid with a certain velocity V. Because of its volume and density, you get rho V. How much momentum is contained in this parcel of fluid? Mass times velocity, right? So momentum would be mass rho v times velocity, right? Momentum contained this mass times velocity. Okay. So if you look at this expression, we have been calling density as just density because that's the only thing we know. But you can think of density as mass density. How much mass is contained in a unit volume? What about this quantity? Rho times V. What is the unit of this quantity? What is the unit for rho times V? What is the unit for rho? Kg per meter cube, right? Kg per meter cube. And if I multiply that with the velocity, meter per second. What is the quantity in the numerator? Do we recognize this? What is mass times velocity? Momentum, right? So this quantity is same unit as momentum. So rho times B can be thought of as momentum density. Just like you think rho is mass density, rho V is momentum density. It's the amount of momentum you transport across the surface when you are flowing. When the fluid is flowing at a certain velocity, it's bringing a mass density of rho. It's bringing a momentum density of rho V. Okay, it's like, sorry for this very weird example. We all walk through the door, right? How many persons we are bringing each of us? One person. I bring myself, you bring yourself, you bring yourself. We all bring one person each. But how many germs we all bring? Allergy season, we are all sneezing. Everyone brings a billion germs, so there are 18 of us. So we all bring a billion germs each and bring 18 billion germs into this room. So it's like saying we bring one of us, but we bring 1 billion germs each along with us. The fluid brings with itself certain density of mass or certain mass density, certain amount of material. It also brings rho times velocity, a certain amount of momentum per unit volume. It could be that it's a dense fluid moving slowly or a light fluid moving quickly. Either case, you will get a high amount of momentum brought in by the fluid. Okay, so rho V is momentum density. So if rho times V dot N dA is mass flow rate, what would be rho V times V dot N dA? What quantity is this? This is mass flow rate. What is this quantity? This is the rate of flow of mass across the surface, mass per second, kg per second. What would be this quantity? What can we call it? This is mass flow rate. What can we call this? Momentum flow, right? So this can be called momentum flow rate. Okay, this can be called momentum flow rate, and if you integrate this over the control surface area, you get the total amount of momentum that is entering this control volume. Okay. You know mass conservation, right? From thermodynamics. What is that? Can you state it? Mass cannot be created or destroyed, right? That's why we wrote what comes in plus what goes out must add up to 0. What is the analogous balance principle for momentum? How do you relate if you have an object and you impart momentum to it? What's the relationship between momentum change and some other quantity that the system experiences? You know this. That's why I'm not saying it.
Talking about conservation movement.
Yeah. What is the conservation principle for momentum? A change in momentum results in what? You have a football or soccer ball and you kick it, you impart momentum. As a result of that momentum imparted, what happens to the ball? Its velocity changes, which is called acceleration, right? So the rate of change of momentum or momentum flow rate brings about an important effect, which is there are forces acting on the system and it's related to how much momentum you bring. So if you have, let's say, a ball and you have a jet of water hitting the ball, because of the momentum transferred, the ball is going to accelerate. So next lecture, what we are going to see is how we relate this momentum flow rate to the force experienced by the control volume. Because in fluid mechanics, everything is about the force, either drag or lift or some kind of force. So we are going to relate this to force. Okay, so we'll pick this up on Tuesday. So my hope is to do this on Tuesday. Hopefully, I'll be able to complete it and talk a little bit about the project on Tuesday or Thursday. For the exam, you will have until everything that's discussed on Tuesday. Whatever we do on Thursday is not on the test. More importantly, I want to talk about the project on Thursday and get you started there. Okay. I haven't said anything else. Is there some preference in the class that you want to do experiment or model? Right? Are there people who say, I want to do experimental work, and are there people who say, I want to do modeling of that experiment? I just want to know. Do you want to do modeling? So there are some numerical people and some experimental people. Can I take? Because instead of letting you form groups and figure this out, I'm going to divide the class into like 6 groups and assign a project. So all of you are going to work on different aspects of the same project. I've thought of that. Hopefully I'll give you more details on Tuesday if it's done. Okay. But think about whether you want to do experiment or simulation.